All right, so there is a rule, there's a rule in Java, if you read the documentation for the object class, that says, if you decide to override equals, you must also override hashCode. Right? The reason you have to do this is because if you don't, anything that relies on hashCode breaks. Okay, so for our point 2 class, for all of our classes so far, we have not replaced hashCode yet. Right? We replaced equals, we haven't replaced hashCode. So in Java, there are what are called hashed containers. So there's something called hash map. There's something called hash set. I didn't tell you about sets and maps yet. Maps are like Python dictionaries. Right? But there are these containers that are called hashed containers. The hashed containers rely on this hashCode method to work properly. So here we've got a point P. Right? So it's the point 1 minus 2. I make one of these hashed containers. So I'm going to make a hash set here. And I'm going to add P to the hash set. Right? So my set of points now has this point P, right? So it has the point 1 minus 2. Right? The sets are useful for testing things like, does the set contain a particular value? Right? The sets also guarantee that they only contain one instance of every value. Right? So no two objects in a set are equal to one another. So I ask the set, excuse me, do you contain the point P? Hopefully the set says yes, because we just put it in. Right? So here it will say yes, I do contain the point P. Now, if you make another point Q, it's a new point, same coordinates as P. Right? And you ask the hash set, do you contain Q? The answer will be false, even though there is a point equal to Q in the set. Right? Yes. I'm going to explain what hashCode is in just a second. Right? The hash, all you need to know for this particular moment in time is that the hash containers use this hashCode method. Right?
It doesn't have duplicated objects.
Yeah, so a set is a set can hold a collection of objects. No two objects in the set are equal to one another. So a set guarantees uniqueness. All right. So this is weird, right? The set has a point equal to Q, but contain says it does not. Okay, so why does this happen? Oops, sorry. All right, so to explain why this happens, I'm going to show you how you might search a collection. Right. Okay, so imagine I don't have a set, but instead I have a list or an array. It doesn't matter. Right. I know that my list or array, it contains only unique points. Right. So all the points have different coordinates. So how do I test whether or not the list contains a particular point? Right. Well, obviously you iterate over the list or array, and you look for an object that's equal to the one you're looking for. Right. So I'm going to write a little method called hasPoint. Right. It takes in a point P. So this is the point that you're searching for. Right. There's your list of points that you want to search. Could also be an array. It doesn't matter in this case. Right. If points contains a point equal to P, this method should return true. If it doesn't, it should return false. How do you write it? Well, you just write a loop. Right. So for each point in the points, if the point is equal to P, notice that we're using equals now, right? Because we've overridden equals. Right? So if point equals P, we can return true. Right? We found a point that's equal to the one that we're looking for. After you process all the points, you know that the result is false, right? We looked at all the points in the list. We didn't find one equal to P, so you can return false after the loop. Right? Okay, so you should know from 121. First of all, you should know how to do this from 121, right? But you should also know from 121 that this is something called linear search or sequential search, right? Or exhaustive search, right? They all mean the same thing, right? For a structure like a list or an array, right? If you double the number of elements in the list or the array, you double the number of potential comparisons you must make, right? So searching a list that's of size 100 takes twice as long as searching a list of size 50 in the worst case. Right? Because you have to look at all the elements in the array or list. So in the best case, you look at the first element and it's the one you're looking for. Right? So the best case of linear search is 01, right? Complexity 01. right? The worst case is ON. You look at all the elements in the list, and none of them were the one that was none of them were the ones was the one that you were looking for. So that's ON. Right? On average, assuming the thing that you're looking for is in the list, right? On average, you'll look at roughly half the elements in the list, right? Which is also in ON. So the worst case complexity of sequential search for a list or array is ON. All right. So the hash containers are magical, right? So you'll learn about this in SIS 235, your data structures course. So there is a way to search a collection of items and determine whether or not something is in the collection in O1 time, so constant time, right? There are certain conditions in which under which you can do this, right? So assuming you're not in one of the unusual situations, right? I claim there is a way to search a collection of items in O1 time to find an item to test whether or not the collection contains a particular object. So in SIS 235, you'll learn all of the gory details of how these things are implemented. I'm just going to give you a very high level idea of what's going on. So there are these things called hash tables. Right? A hash table you can think of as just being an array or list of buckets. Right? Every bucket can hold multiple items. Right? So in an array or list, each element holds one thing. In a hash table, your elements are buckets. The buckets can hold more than one thing. Right? So here's a hash table that has n plus 1 buckets, right? They're numbered 0 through n. Okay, so if you've got a hash table, the way these work in Java is you take an object, right? You give it to the hash table. You say, hey, I want to add this object to the hash table. The hash table takes your object and calls this hashCode method. Right? So hashCode returns an int. Right? The purpose of hashCode is to take an object and convert it to some integer value. Right? How does it do it? It doesn't matter how it does it. Right? The basic idea is you're going to look at the fields of the object and do something with the fields, and so combine the fields somehow and get back an int result. Right? So you don't actually care how it does this. All that you care about is that hashCode returns an int that maps it takes an object A, maps it to an int. Right, that int value is used by the hash table to figure out which bucket should it put the object into. Right. Okay. So remember, ints are negative, right? They're signed, so they can have a negative value. The hash table's buckets are labeled 0 to n. So after calling hashCode, the hash table has to do something to the int value to make sure it gets mapped into the range 0 to n. So that's what this red arrow here means. Right? Hash table takes your object that you're adding to the hash table A, calls its hashCode method, does something with the int so that the int is in the range 0 to n. Again, all of these details are discussed in SIS 235. So here we called hashCode, got an int value. The int value got turned into 2. So the hash table takes A, sticks it into bucket 2. Like that. If you put another object into the hash table, right? So we're going to put B into the hash table. The hash table takes your object B, calls hashCode. Hashcode returns an int value. The hash table turns that int value, in this case, to 0. So it puts B into bucket 0. Right? C gets mapped onto N. Come on. Right? And D, in this case, also gets mapped onto N. It doesn't mean that D and C are equal. All it means is that D and C have the same hashcode. Right? So that gets put into the bucket N. All right. So after you've put all the elements into your hash table, ideally, right, the elements in the hash table, the distribution of the elements in the hash table is roughly uniform. Right? In other words, every bucket holds more or less the same number of items. Right? Roughly. It's not exact, right? Roughly. So here, all of the buckets hold like 0, 1, or 2 elements, which is great. Oh, sorry. Oh. Okay. So now we've put some elements into the hash table. How does the hash table search for an element? Well, it just repeats the process all over again. Right? So if we want to know, is A in the hash table, the hash table takes A, calls hashCode, does something with the value, turns that into 2, right? So now it knows to go and look in bucket 2, right? Now there could be multiple items in bucket 2, right? And so it now searches, and now it calls equals on every item in the bucket. Right? So here we're searching for the object whose value is equal to A. Right? So here we're going to use A equals and then the object in the bucket. Right? So in this case, it's true. So the hash table says, yes, I do in fact contain the object A. Oops, sorry, that's true. So what happens if we take Z? Right? So Z is a different, sorry, the value of Z is different from A, B, C, or D. Right? So it's not equal to any one of those. So we ask the hash table, hey, do you contain the value Z? Right? So hash table takes Z, calls hashCode on it, does something with the int, turns it into N. So now the hash table goes and looks at all of the items in bucket N. Right? Is Z equal to C? The answer is no. Is Z equals D? The answer is no. Are there any more items in the bucket? The answer is no. Therefore, the hash table says it does not contain Z. So it returns false. Okay, so assuming you implement your hash table well, then searching a hash table turns out to be much faster than linear search, right? So on average, right, you end up searching for an element in a bucket that holds a small number of elements or a fixed number of elements, right? The fixed is important. So if you are searching a fixed number of elements and the fixed number is not proportional to the size of the list, the hash table, sorry, right, then that turns out to be in O1, right? And so that's how these data structures are able to perform operations like search very quickly compared to a data structure like a list or an array. Okay, so all of this though relies on hashCode working, right? Or hashCode doing what it's supposed to do. So what exactly does hashCode do? Right. So first, remember, where did hashCode come from? It came from big O object. Right. What does the big O object version of hashCode do? It looks at the memory address of the object, or somehow it gets the memory address of the object and uses that or converts that to a hashCode. Right. So remember, it uses the memory address of the object, or it uses the identity of an object to compute its hashCode. Why is that a problem? Right. So here we've got a point P. It's a new point, right? Here is point Q. It's a new point, right? P and Q cannot have the same memory address, right? Only one object lives at any address, so they can't have the same memory address, right? What does that mean? It means their hash codes are probably different, right? So the hash code of P is different than the hash code of Q. Right? The 2 points are equal, right? Their coordinates are 1 and -2. Because we changed the definition of equals, right? But their memory addresses are different. We haven't changed the definition of hashCode. So hashCode for P probably returns a different hashCode than Q. Right? So P and Q are different objects. Therefore, their memory locations are different. We haven't changed the definition of hashCode. So hashCode is going to use the memory addresses to compute the hashCode. Therefore, their hash codes are probably different, almost certainly, but not guaranteed. Right? And therefore, what ends up happening is the hash table probably goes and looks in the wrong bucket when it goes to look for the object. Right? So in other words, when you ask, does it contain Q? Right? It goes to a different bucket than where it put P. Right? And so now it looks in that bucket, it doesn't find Q, and it returns false. Sorry, that's again, that's a cut and paste error. That's the point, not the complex number. Right. Okay, so there is the very long-winded explanation of what hashCode does and why you have to replace it if you replace equals. Right. So we replaced equals for points. Right. Now our version of equals is no longer consistent with our version of hashCode. So now I have to go and replace our version of hashCode so that it's consistent with equals. Okay, so what do I mean by consistent with equals? So what I mean is if x equals y is true, right? two objects are equal, then it must be the case that their hash codes are now equal, right? If they're not, right? So in other words, if you override hash code, you have two equals objects and they return different hash codes, all of the hash containers are going to break, right? When they put something into the hash table, they will put them into different buckets. So when they go to search for them, they will search in different buckets, right? So if you replace equals, you have to replace hash code so that if two objects are equal, their hash codes are also equal, right? Similarly, hash code can't be random, right? So you can't randomly return an integer value for hash code, right? If it's random, hash tables are going to jump in random locations whenever you ask for or put an object into the hash table. So if you don't change the state of x, x.hashcode must return the same value every time. All right, so how do you generate a hash code? So it turns out generating a hash code is not a simple process. Right? Sorry, generating a good hash code is not a simple process. Right? There is a notebook for hash code that tells you what the recipe Eclipse uses. It's not important that you know the recipe. All that you need to know is that you need to take the fields of your object, somehow convert them to an integer value. Right. Now, when you do this, it would be nice if you have two objects that are not equal, that they produce different hash codes, right? If you think about this for a minute, though, you realize that you can't actually do this, right? So it's not required. If you have two unequal objects, they are allowed to produce the same hash code. So here's point 2. Again, these should be double, right? Not float. Okay, so why can't you guarantee that if two objects are not equal, they have different hash codes, right? So every point has a double X and a double Y, right? How many unique combinations of X and Y are there? Well, there's 2 to the 64 values of X. There's 2 to the 64 values of Y. There's 2 to the 128 values of X and Y. How many ints are there? Well, there's only 2 to the 32. Right? So there's no way that I can convert X and Y to some int value and guarantee that 2 points that are different, not equal, have a different hash code. Right? There's going to be lots of points that are not equal that have the same hash code. Right? This is what you definitely should not do. Right? You should not override hash code to return a constant value. Right? Why not? Right? So this is always going to return 1. So when you put points into a hash table, right? All the points get put into the same bucket. If you put everything into the same bucket, it's like putting something into a list, right? So now your O1 search becomes ON because you have to search all the elements in the bucket now, right? So this is a terrible hash code. Don't do this. This is also a bad hash code, right? So for values of X and Y that are close together, this always produces the same hash code. Right. So imagine you're writing some application. All of your points have coordinates between 0 and 1. Right. This will put all of the points into one of 3 different buckets. I think 0, 1, or 2. Yes. Right. So this will put all the points into one of 3 different buckets. Again, bad idea. Right. Don't do it this way. How should you do it? So there's a class called Big O Objects with an S. Right. This is the utility class that's paired with object. Right? So it contains a bunch of methods that operate on big O objects. Right? That's why the S is important here. Right? Objects has a function method called hash. You can pass as many values as you want to hash of any type. And objects.hash will compute a hash code for you. So if I want to compute a hash code using the X and Y coordinates of a point, right, simply pass in the X, Y coordinates of the point, and objects.hash will generate a hash code for you. Right. So this is the way you should implement hash code in this course. Oops, sorry. Equivalently, you can ask Eclipse to generate hash code for you. Right. So the Eclipse version of hash code will, I think in new versions of Eclipse, it produces this. I think. In older versions of Eclipse, it does something else. Right. So the older versions of Eclipse, you can read that quote there, and it roughly tells you what it doesn't exactly tell you what it does, but it tells you that what Eclipse does in practice works, but is not guaranteed to work depending on exactly what your object is and what you're using the hash table for, and what kind of objects you put into your hash table. Right. And so it turns out doing this operation where you convert an object into an integer value turns out to be very useful, not just for storing them in a hash table, but in fields like cryptography or other things like that, or computer security. This turns out to be a very useful thing. Right? If you know what an MD5 hash is, this is all related to that. If you don't know what it is, don't worry about it. It's fine. Right. So people do study how to generate or how to algorithms for computing hash codes. All that I care about is that you know why you have to generate hash code, right? Why you have to implement hash code, right? When you need to do it, you just write something like this and everything's fine. I guess there's one other thing I should tell you. Okay. You have to be careful about this requirement right here. Right? So if x equals y is true, then the hash codes must be equal. Right? So remember what you do in equals. You compare the fields of an object. Sometimes in equals, you don't compare all the fields. Right? Some of the fields might not be relevant for equals. Right? So if you leave some fields out of equals, you have to leave the same fields out of hash code. Right? So for example, suppose for point 2, we said 2 points are equal if and only if their x coordinates are equal. Right? So 1, 0 is equal to 1, 2. Right? Doesn't make sense, but let's suppose that we decided to do it that way. What happens if you leave x and y in your hash code method? Right? So 1, 0 is equal to 1, 2. When I call hash code, 1, 0, right? And 1, 2, right? Objects.hash is going to produce a different hash code for those pairs of values. Right? So now you have two objects that equal says are equal, but hash code says is not. Right? They return different hash codes. So whatever fields you use in equals, those are the fields you plug in here. If you leave some fields out of equals for some reason, you leave the same fields out of hash code. Right? If you don't, your hash code method is broken. It's not consistent with equals, right? And all of the hash containers now break when you try to use them.